Okay, I'm Katie Wooddell, and today I will be presenting the version 1 ground motion logic tree structure. So this summarizes the questions that were posed by the TI team. The first of these deals with the structure of the version 1 ground motion logic tree, in particular how it compares to the version 0 logic tree that was presented last March. So I will begin this presentation by summarizing the version 0 ground motion logic tree, and then the remainder of my talk will focus on the changes then to the ground motion 1 logic tree and how it has evolved since last March. One point I want to make about the version 1 logic tree, when I show it, you won't see any weights on the branches. And that's because it's through the interrogation of our proponent experts here that we'll gain insight into the strengths and the limitations of some of the models on these branches. And then after this workshop, we'll be able to make judgments and start applying weights to these branches. The sensitivity analysis of the version 1 logic tree will be presented in the following presentations by Nick Greger and Melanie Walling. And for these sensitivity analysis, a weight of 1 basically has been assigned to each branch, and then the hazard has been computed for the version 1 logic tree. And then those hazard results are compared to the hazard results that come out of the version 0 logic tree. So in this sense, the version 0 logic tree is our base case. And that'll be discussed further by both Nick and Melanie. And the second and third bullet points here relate to the limitations of the version 1 logic tree, and also the potential ground motion characteristics that have not yet been captured in the version 1 logic tree, and I'll reserve that for the last slide. Okay, Nick just discussed this. I'll go kind of quickly through it, but these branches represent the ground motion models from then the version 0 logic tree. So we used the 5 2008 NGA models. Each of the models received equal weight in this logic tree. And for the base case parameters that we input into those models, we used a reference site condition of with a VS30 of 760 meters a second. And then Z 1.0 and Z 2.5 values were chosen to be appropriate for that reference site condition. We used a maximum of 4 standard deviations above the median for the ground motion models. This was selected because early on when we did the sensitivity analysis, we saw that at the 10 to the minus 4 hazard level, an epsilon max of 4 yielded the same results as the epsilon max of 5, and we went with 4. This set of branches addresses the additional epistemic uncertainty that is added. So the idea behind adding additional epistemic uncertainty is that typically when you address epistemic uncertainty, you assign weights to alternative independent models. But the NGA models are not necessarily independent. They were developed as part of a collaborative effort, and they all started with the same initial database of earthquakes. So whenever using the NGA models, additional epistemic uncertainty should be applied. And this particular epistemic uncertainty model came out of the work that, an analysis that Bob Youngs did in 2009. And he looked at the standard deviation of a single NGA model, and he also looked at the variability between the standard deviations of the suite of NGA models. And based on his conclusions, we came up with these 2 epistemic uncertainty models for application to Diablo Canyon. And the first of these here addresses the fact that the NGA models are not independent, so we've added additional epistemic uncertainty, but it also addresses the fact that all of the median predictions for the NGA models are similar for large magnitude strike-slip earthquakes at short distances. And by short distances, we're talking like within 10 kilometers. And the other model, this model I want to mention was applied for the Hosgri fault. And the other model was applied for the other faults in our seismic hazard, And it accounts for the fact that again, the NGA models are not independent, and it doesn't add quite as much epistemic uncertainty because the variability between the NGA models already accounts for this. I won't say much about the sigma model because in the version 0 model, we just used the ergodic approach for the standard deviations, and the GMPE specific values as published with the 2008 models were used, so not much to talk about there. Okay, this is the structure then for the version 1 ground motion logic tree for the median. And I'll deal with each of these components separately in the following slides, but I just want to provide some of the major differences then between this model and the version 0 model. So the first set of branches here on the left represent the ground motion prediction equations that are used. And Nick already went through those, but the main difference that's immediately obvious is we have expanded our list of candidate models. The second branch deals with this additional epistemic uncertainty here in the middle. Due to our expanded scope, we need to expand how we're dealing with the epistemic uncertainty. So we need models that can be applied for different mechanisms and over a variety of magnitude and distance ranges. And then the last two branches deal with how we're going to compute ground motions for the complex rupture cases and the splay fault rupture cases. So we have all these ground motion prediction equations, but when our ruptures become more complicated, it's not always clear what parameters we're going to plug into those ground motion prediction equations. So these last two branches all deal with different methods for coming up with which parameters to plug into those GMPEs. Okay, so specific changes for the candidate GMPEs. We have replaced the 5 2008 NGA models with the updated 2013 NGA models. And 4 additional candidate models were added, which Nick has already discussed. And down here at the bottom, you'll see another little branch here, and that represents the finite fault simulations. And they're kind of hanging out down there by themselves because they can be dealt with in one of two ways. One way we can deal with these simulations is we can parameterize them into a GMPE and then evaluate them along with the rest of the GMPE models. Or we can simply use these models to then look and see if the suite of candidate GMPEs is producing the correct range of ground motions. Okay, this is showing the changes that have been made in the additional epistemic uncertainty models. The main changes include, again, developing epistemic uncertainty models that can be applied for different mechanisms and across a variety of magnitude and distance ranges. And we're going to capture the ranges based on epistemic uncertainty visualization. I'm not going to go into that now. That's going to be discussed, I believe, tomorrow by Nico Kahn. So wait till tomorrow on that topic. Okay, so then this branch deals with how we're going to compute or how we're going to use the GMPEs to compute ground motions for the complex rupture case. So here on the left, I have a figure that looks very similar to the figure Jennifer just showed. And it's an example of a complex rupture involving the San-Simeon fault in blue, the Hausgry fault in green, and the Los Osos fault in red. And this is a complex rupture because imagine an earthquake is initiated on that San-Simeon fault and ruptures down to the Hausgry, and from the Hausgry ruptures onto the Los Osos fault. The San-Simeon and Hausgry faults are 90-degree beam faults, and then when the rupture crosses over to the Los Osos fault, it's jumping onto a segment that has a dip. I think in this case it has a dip of 60 degrees. Also, the San-Simeon and Hausgry faults are right lateral strike slip, so they have rakes near 180 degrees. And the Los Osos is a reverse fault with a rake of about 90 degrees. So this is a complex rupture. This yellow star right here is the location of Diablo Canyon. So at our location, the big question is, which rake and which dip do you input into the GMPE? There are two approaches that have been taken by the NGA modelers, And one of those approaches is to compute an average rake and average dip weighted by the length over the entire fault, and then use the closest distance between our point of interest, Diablo Canyon, and the average parameters of that fault to compute the ground motions from the GMPE. The other approach that could be taken is that you can simply use the closest distance between Diablo Canyon and the nearest segment, which in this case is a reverse fault with a dip of 60 degrees to compute the GMPEs. So in case one, you're using a rake that's closer to 180 degrees, so you probably will end up with a strike-slip fault and a dip that's more vertical. And in the second case, you'll end up with a 60-degree dip on a reverse fault. Those will result in different ground motions. And I forgot to mention in each case, then the magnitude is based on the length of this entire fault. And then there are other approaches. You could take a fault average and instead of weighting it by the length, weight it by a parameter such as 1 over r. Or you could look at finite fault simulations and develop factors that can then guide you in adjusting the GMPEs. So it really matters how we compute the parameters that we stick into these GMPEs. I won't go over this because this is just a bunch of bullets describing what I've just basically said. Okay, so this is an example then of a splay fault, and it's a little bit different than the complex rupture because in the splay fault, again using the example of San Simeon, Hosgri, and Los Osos. So in a splay fault, let's assume that a rupture starts on the San Simeon, propagates down the San Simeon and Hosgri, and when you get to this junction, it simultaneously continues to rupture down the Hosgri and it goes on to this splay fault. So there are two main ways now of treating this scenario, or treating this system. One way is you can treat this thing as one big earthquake. So if you're at Diablo Canyon, what we could do is we could compute a magnitude based on the summed moment of the main fault and the splay fault. Then we could use the closest distance to whatever segment. So we would use whatever distance is closer, the distance either to the splay or the distance to the main rupture. In this case, it would be to the splay. And then we could use fault parameters, dips and rakes, that are averaged along this entire fault. Or we could use fault parameters, the dip and the rake of the nearest segment. So we'll end up with different ground motions in either case. The other way we could do it is we could treat this as two separate earthquakes in the GMPEs. We could model, we could model the main fault as one earthquake in the GMPE and use the closest distance to the main fault and either the average parameter along the main fault or, I don't know, the parameters to the closest segment. In this case, they're the same, thank goodness. And then we could use, the GMPEs to compute ground motions for the splay fault using the closest distance and the strike and dip of the splay fault. And then we would sum the GMPEs using the SRSS method, the square root of the sum of squares. And then we also have factors that we can develop from the finite fault simulations, and these hopefully can guide us to help us determine which of these methods is the most appropriate to use. Okay. Then last, we have the ground motion logic tree for the aleatory variability. And Linda's going to be going into this in a lot more detail on Thursday. But the main changes between the version 1 logic tree structure and then the version 0 is that we're going to include single station sigma. So we're going to bring that along. And Linda's going to discuss the different models. There are different models for the FESS, so that's the single station within event variability. There's a constant model, a model that's dependent on both magnitude and distance, and a model that is just magnitude dependent. And then there's the tau model, which is the which represents the between event variability. Previously, we just used GMPE specific values. Now we're going to look at some global averages, and we will add epistemic uncertainty into these global average models. And again, this will be discussed in more detail by Linda on Thursday morning, I believe. Okay, so what are the limitations and the ground motion characteristics that have not yet been captured in our version 1 ground motion logic tree? The first deals with the median model. 2 of the European models have not yet been included, and the third bullet point actually goes with the first bullet point. And these will be considered in a presentation by Ekar. And the median model, we haven't included the Zhao 2011 magnitude scaling concept. In terms of the standard deviation model, we haven't addressed directivity effects. So these haven't been included, and they're going to be discussed in this next workshop, or this workshop. So I'll leave those there, and I'll take any questions if there are any.
I have a quick comment. In your presentation, you mentioned it's a Bindi 2013 in the logic tree. I think that is a Bindi 2011, so it will be worth it to correct that. Yeah.
I noticed that when Nick was
Okay.
giving his presentation, but
Okay.
thanks.